Hello! In this video, we are going to prove the following theorem. Let S be a finite subset of positive integers with n elements. Then there exists a function f from in to s such that f of I plus 1 is greater than f of I is greater than or equal to I for all integers I such that 1 is less than or equal to I is less than n. Now in this theorem, we are using the notation in, which refers to the set of integers between 1 and n. For example, I0 is the empty set, I1 consists only of 1, I2 consists only of 1 and 2, and so on. Now, what this theorem is essentially saying is, we can take any finite set of positive integers, and we have a way of listing its elements in order. Now, in proving this theorem, we are going to use induction on the number of elements in S. So let's start with the base case. In the base case, we're trying to prove that the theorem is true for any subset of positive integers with 0 elements. So let's consider an arbitrary subset of positive integers with 0 elements. I'll call it S. From here, we want to find a function f from I0 to S with this property. Now, since the number of elements in S is equal to 0, this tells us S is an empty set. Also, from earlier, we saw that I0 is an empty set. So really, we're trying to find a function from the empty set to the empty set, which has this property. Now, the empty set is a function from the empty set to the empty set, and no matter what we choose our function to be, this statement will be vacuously true, because there is no integer I such that 1 is less than or equal to I is less than 0. So if we take this function to be the empty set, then that's a valid choice. So this completes the base case. Now let's move on to the induction step. In the induction step, we give ourselves an arbitrary integer n greater than or equal to 0. And we assume that the theorem is true for all subsets of positive integers with n elements. And now we want to show that the theorem is true for all subsets of positive integers with n plus 1 elements. So to do that, let's consider an arbitrary subset of positive integers with n plus 1 elements. I'll call it S. From here, the whole goal is to find a function f from in plus 1 to s, which has the property that f of I plus 1 is greater than f of I is greater than or equal to I for all integers I, such that 1 is less than or equal to I is less than n plus 1. Now, since S has n plus 1 elements in it, well, n plus 1 is greater than 0, so S is non-empty. Therefore, S is non-empty and finite. And actually, every non-empty finite subset of positive integers has a largest element. In fact, that's also true for any non-empty finite subset of real numbers. So S has a largest element, and I'll call that largest element B. So now let's consider what happens if we take the set S and remove B from it. We're going to call that new set T. Now, since we've taken the set S and we've removed B from it, this means T should have n elements in it. Now, T is a subset of S, and S is a subset of the positive integers, which implies T is a subset of the positive integers. Therefore, T is a subset of the positive integers with n elements. But remember, we're assuming that the theorem is true for all subsets of positive integers with n elements. So it must be true for T. Well, in that case, that means we can find a function I'll call g from in to t with a property that g of I plus 1 is greater than g of I is greater than or equal to I for all integers I such that 1 is less than or equal to I is less than n. Now remember, the whole goal has been to prove the theorem for all subsets of positive integers with n+1 elements. And at this point, we have given ourselves a subset of positive integers with n+1 elements, namely s. And we're trying to find a function f from in+1 to s with the property that f of I plus 1 is greater than f of I is greater than or equal to I for all integers I such that 1 is less than or equal to I is less than n+1. And we're going to define that function right now. The function is essentially going to be g with b added onto it. We consider the function f from in+1 to s, and it's defined as follows. Given any integer I in in+1, we will assign f of I to g of I if I is between 1 and n. Otherwise, we will assign f of I to b if I is equal to n+1. Now, this definition makes sense because if we consider any integer I in in+1, then exactly one of these conditions is true. And no matter which condition is true, the output value that gets assigned to it is going to be an element of S. Because on one hand, we know that B is an element of S, and all the output values of G are elements of T, which is a subset of S. So now, let's show that this function has the desired property. We want to show that f of I plus 1 is greater than f of I is greater than or equal to I for all integers I, such that 1 is less than or equal to I is less than n+1. So to do that, let's give ourselves an arbitrary integer I, such that 1 is less than or equal to I is less than n+1. Well, since we're working with integers, to say that I is less than n+1 implies I is less than or equal to n. And the whole goal is to show that f of I plus 1 is greater than f of I is greater than or equal to I. And to show that, we're going to split this up into two cases. Either I is less than n or I is equal to n. Let's first consider the case I is less than n. If I is less than n, well then we have 1 is less than or equal to I is less than n. And because this inequality is true, well, let's go to the fact that we know about our function g. This statement works for all integers that satisfy this inequality. So in particular, it must work for I. Therefore, we have g of I plus 1 is greater than g of I is greater than or equal to I. Also, we know I lies between 1 and n, so f of I is going to be equal to g of I. But these inequalities imply that I plus 1 also lies between 1 and n, so f of I plus 1 is going to be equal to g of I plus 1. So we can substitute g of I plus 1 with f of I plus 1. We can substitute g of I for f of I. So we have f of I plus 1 is greater than f of I is greater than or equal to I. And so we're done. This completes the case I is less than n. Now let's consider the case I is equal to n. Well then, in this case, again, we know that I lies between 1 and n. So f of I is going to be assigned to g of I. And we know that g of I is an element of t. And all elements of t are not equal to b. So g of I is not equal to b. But since I is equal to n, that implies I plus 1 is equal to n plus 1. So f of I plus 1 is going to be assigned to b. Now since b is the largest element of S, this means that b is greater than or equal to every element of S. So in particular, b must be greater than or equal to f of I. But since b is not equal to f of I, this tells us b must be strictly greater than f of I. And let's remind ourselves, b is equal to f of I plus 1. So this shows f of I plus 1 is strictly greater than f of I. Now, all that's left to show is that f of I is greater than or equal to I. And to show that, we're going to consider two more cases. Either I is equal to 1 or I is greater than 1. Let's first consider the case I is equal to 1. What happens if I is equal to 1? Well, we know that f of I is an element of S, and S is a subset of positive integers. So f of I is a positive integer. And all positive integers are greater than or equal to 1, so f of I is greater than or equal to 1. and 1 is equal to I. So this shows f of I is greater than or equal to I, so we're done. This completes the case I is equal to 1. Now let's consider the case I is greater than 1. If I is greater than 1, then since we're working with integers, this implies I minus 1 is greater than or equal to 1. And I minus 1 is less than I, and I is equal to n. So this shows 1 is less than or equal to I minus 1 is less than n. So, using the fact that we know about the function g, if we replace I with I minus 1, we get that g of I is greater than g of I minus 1 is greater than or equal to I minus 1. And from earlier, we know that f of I is equal to g of I. So this shows f of I is greater than I minus 1. And since we're working with integers, that implies f of I is greater than or equal to I. And so we're done. We see in either case, whether we have I equal to 1 or I greater than 1, it follows that f of I is greater than or equal to I. And so we have f of I plus 1 is greater than f of I, which is greater than or equal to I. So this completes case 2. And now we see in either case, we have f of I plus 1 is greater than f of I is greater than or equal to I. And we have shown that this inequality is true for an arbitrary integer I, such that 1 is less than or equal to I is less than n plus 1. And therefore, we have shown for all integers I, such that 1 is less than or equal to I is less than n plus 1, it follows that f of I plus 1 is greater than f of I, which is greater than or equal to I. And that's exactly what we wanted to show. So we have shown, given any subset of positive integers s with n plus 1 elements, there exists a function f from in plus 1 to s with this property. So we have shown that the theorem is true for all subsets of positive integers with n plus 1 elements. So this completes the induction step. Because we've completed both the base case and the induction step, this closes the induction. So we have proven the theorem for all finite sets, no matter how many elements are in them. And so this completes the proof. And also, a property that we have proven regarding functions with this property is the following. We have for all integers p and q in In, if p is greater than q, then f of p is greater than f of q. And this immediately tells us that f is injective. Because it is certainly true for all integers p and q in In, if p is not equal to q, then f of p is not equal to f of q. So f is injective, but f is an injective function from In to s. And In and s are both finite sets with the same number of elements. So that implies f must be surjective as well. So f is a bijection from In to s. And so yeah, that's pretty much it for this video.